Hello, my name is Gilbert Maystre, and I will be talking about our recent results on the structure of the TFNP hierarchy. This is joint work with William Pires, Robert Robira, and Ram Tao from McGill, Alexandros Hollander from Oxford, and my colleagues at TPFL, Mika Yus and Siddhartha Jain. As a warm-up, let me define the TFNP class. So TFNP is the set of all total NP search problems. So in search problems, you actually have to find a solution, not merely decide whether one exists. For instance, given a formula, you need to find a satisfying assignment. This class starts to be interesting when the problem you're looking at always admits a solution. This would make a decision problem moot. So more formally, a search problem is a relationship on bit strings. So it's a subset of the Cartesian product of bit strings. We say that a search problem is total if for any x, you can always find a y such that the relationship holds. And we say that y is a solution of the instance x. We say that a search problem is in NP if furthermore, this y always has size polynomial in x, or can always be made small, and that you can also check the relationship in time polynomial. So example of TFNP problem include factoring. You're given an integer and you need to find its prime factors. Note that this is total, and it's also in NP, because you can always check that the prime factors are indeed prime, and that multiplying them, you get your initial number. Other problems include finding a Nash equilibrium and more. So how do we reduce problem within TFNP? So we say that a problem A reduces to a problem B. This is the definition of many one reduction if there exists a pair of polynomial time computable function f and g, such that given an A instance x, you can pass it through f to get a B instance y. Then you have a solver somewhere in the cloud that could solve the B instance y. You get a solution z. Note that there might exist many of those z that are solution for y. And then you have G that can convert the B instance solution Z to an A instance solution S. And this needs to work for all Z that are solution to Y. This is a natural way of defining reductions, many one reduction. So now that we know how reduction work, we can talk about complete problem. The thing is, it's unlikely that TFNP has a complete problem. This is because TFNP is a semantic class. So to revert to that, we study subclasses that are aggregating problems by the principle that guarantees their totality. Recall that in TFNP, all the search problems are total. That is, they always have a solution. For instance, the class polynomial local search rely on the principle that every acyclic directed graph has a sink. The class PPP is based on the pigeonhole principle and use the fact that any map from n+1 object to n object must have a collision. Another example would be the class PPA, which says that every matching on an odd number of vertices must have an unmatched vertex. Okay, so let me now show in more detail how we formally define, for instance, the PLS class. So the PLS class for polynomial local search is defined with a complete problem called sink of DAG. So recall that the PLS class, the principle behind it was that every acyclic directed graph had a sink. But right, if you're given a graph, then it's easy to find a sink. The idea is that we're going to look at an exponentially sized graph, but which is defined in an implicit and small way. So to make this formal, we have two circuits, S and L for successor and level, which are mapping bit strings of size n to bit strings of size n. And we say that those implicitly represent a directed acyclic graph G. The vertex set would be all the bit strings of size n, So the vertex set is of exponential size. And the edge UV appears in G if and only if the successor of U is V. So the successor of U in the circuit is V. And also the level of V is strictly larger than the level of U. So this ensures that the graph is indeed acyclic. And now a solution is any sink in this implicit graph G, or the all zero string if it's not a source. This is just to make the problem total, right? And to avoid the problem where the graph has no edges at all. So pictorially, here is the deal. So we're given two circuits, successor and level, taking bit strings of size n and putting bit strings of size n. And this implicitly corresponds to a graph on 2 to the n vertices. And now you need to find a sink in this graph, right? Note that you could have several paths that merge in one vertex. Okay. And now that we have this problem sink of DAG, which is in TFNP, we just define PLS as being the subset of TFNP, which is reducible to sink of DAG. And it's clear that sink of DAG is complete for PLS. Let me give you yet another example for the PPAD class. So the complete problem here would be end of line. So you're given two circuits, successor and predecessor, which are implicitly representing a directed graph G. The vertex set is again of size exponential, and there is an edge between U and V if the successor of U is V and the predecessor of V is U. And now you can output a sink. Now solution is a sink of G or zero, the all zero string if it's not a source. Note that this time you can also have cycles in your graph, but you will always find a solution. By the way, in this talk, the solutions are always depicted in dashed red. Finally, the class PPAD is simply defined as the subset of TFNP that can be reduced to end of line. Okay, so you can do this for many complete problems, and you get kind of a hierarchy of TFNP subclasses. And this is how it used to look like at the start of this research direction. So you had three classes, PLS, PPP, and PPA on top, and then subclasses. For instance, PPAD is a subset of PPA. Okay, at the bottom, there is FP, and it's anything that is actually efficiently computable. So you can actually find a solution in polynomial time. You don't. Yeah. So this hierarchy was really good at classifying problems. For instance, Nash is complete for PPAD, so finding a Nash equilibrium. PPA holds many problems like third division, also the Smith problem. PLS holds a max cut and all kinds of local optimization problem. PPP is related to cryptography, etc. But frustratingly, there were important problems like gradient descent that couldn't fit in one of those classes only. So gradient descent was shown to belong to both PLS and PPAD, so the intersection of both. But this PLS intersect PPAD class is not very natural, right? We will see what a complete problem for this looks like later. But let me just say that people were not very happy about this intersection class. And those problems are interesting, right? Gradient descent, finding a fixed point due to Banach theorem, etc. So a bit later in 2011, Das, Kalakis, and Papadumitriou invented the class CLS for continuous local search, and basically put those two problems in this class. This was not super satisfactory because CLS depends on, is defined on arithmetic circuits, and it was not very clean. So to understand the true power of CLS, new classes, new subclasses like end of potential line and unique end of potential line were introduced by Hubasev, Yogev, Fernley, Gordon, Mehta, and Savani. That was 2020. And those were fully combinatorial. Okay. Then in 2021 came the breakthrough collapse that actually explained that PLS intersect PPAD was indeed an interesting class, and that basically because it's equal to CLS. So that was kind of a shock in the community, I guess, and it was very surprising to us also. So this is where our work started. And we were wondering whether we could find any other collapse or prove against collapse. And in this talk, we have two new results, and those are two new collapse results. So first, we show that the intersection of PLS and PPADS is equal to the so-called class sink of potential line. So this might not seem like a very interesting class at the start, but it's essential in the proof of the OPL collapse, which is our second and more surprising result, is that PLS intersect PPAD not only collapses to CLS, but it actually collapses even down to end of potential line. So this was really surprising to us because we're first trying to show that the collapse could not go further, or under likely assumption could not go further. Okay, and also our result is very elementary. So we will see the whole proof in about 10 minutes, and it directly implies the CLS collapse. So this is also nice. Okay, so let me say more on our result that PLS intersect PPAD is a subset of end of potential line. And I will present it in three crux ideas. So the first idea is to take a grid view approach of TFNP, right? All those TFNP problems are based on circuits of representing objects of exponential size. And the idea was that we needed some common language to reason about them and assemble them to get our collapse. So this new meta problem, in some sense, we call it the grid problem. So we're given a grid of vertices with n rows. You should think of n as being exponential, right? And m columns. You can also think of this as being exponential, although it's not that important. Okay. You're also given distinguished sources in green and distinguished sinks in blue. And the constraint is that there are more sources than sinks. Okay, now you have a circuit that for each vertex designate its successor in the next column. And it could also be null. So that would mean no successor. And this circuit is of small size, and it describes implicitly a graph of exponential size. Now I need to describe what the solutions are, and it would be any non-distinguished sinks. Because we have more distinguished source than sinks, then we will always find a solution. Also, a distinguished source, which is not a source, would be a solution. Now, here are ways to tweak this grid problem. We can also add a predecessor circuit, which matches the successor circuit and allows us to backtrack in the instance. And also we can decide to add new kinds of solution. So without further ado, let me show how this grid problem can be messaged to be a complete problem for several classes in TFNP. So first, for the end of potential line, the problem would be as follows. We would have one distinguished source and 0 distinguished sinks. We would also have predecessor circuits in addition to the successor circuit. And we need that those two are syntactically, we ensure syntactically that those two matches. And we also allow sources, so undistinguished sources, as solutions, right? So for people that are familiar with end of potential line, you might be worried that we actually have no potential circuit. But the thing is that it's hidden in the column structure of the problem. Okay. So this end of potential line problem is complete. We define it as the complete problem for end of potential line. Now for sink of potential line, it's exactly the same as before, but now we don't allow for undistinguished sources to be solutions. Perhaps more interestingly, there is also a grid problem which is complete for PPAD. So recall that we saw a definition for PPAD earlier. And here we have another complete problem. So we would have here two columns, a pigeon column and a whole column. And indeed, we put the whole first column as the pigeon column, and it would have n sources. And the whole column would have n-1 sinks. Now again, in addition to successor pointers, we also have a predecessor pointer, so a circuit computing the predecessor. And for solution, it's as usual, any sources, any indistinguished source which is not a source. So here it would be a map pigeon, and also empty holes. This is what makes it a bijective pigeon. So yeah, you can show that this problem is actually complete for PPAD, and so we can use it for our construction. We will see later how this goes. So this was the first idea, is to define a unifying view of TFNP so that we can mix and match problems together. And it seems that this grid structure is a really good way to do it. And you can also define complete problems, for instance, for PLS, for PPA, for PPADS, etc. Most problems admit a grid definition. Okay, the second idea is to use our first collapse, right? To use the PLS intersect PPADS is equal to SOPL, so that as PPAD is a subset of PPADS, it's only enough to show that sink of potential line intersect PPAD is a subset of EOPL. That is, we take a complete problem and we transform it, complete problem from sink of potential line intersect PPAD, and we transform it into an end of potential line instance. So the unique, the natural, I mean, it's not natural, but okay, the easy complete problem for SOPL intersect PPAD is to take, so you get two instances. One instance is sink of potential line, and the other instance is bijective pigeon. So note that you get an SOPL complete instance, a problem, and also PPAD complete problem. And now you just need to output a solution to either of the problem. Any you like will do. And you can actually show that this either construction is complete for the intersection class. It's not too hard. So the only thing we need now is to show that either sink of potential line and bijective pigeon reduces to end of potential line. As a starter and warm-up, we can try to do it with sink of potential line only. So, right, remember what was the difference between sink of potential line and end of potential line? Well, the only difference is that sources are end of potential line solution as well, but they're not solution in the sink of potential line instance. So a quick fix would be to do this reduction. You take your original instance and you take a reversed copy where the flow is in the other direction, and now you just link it naturally. And you call this your end of potential line instance, right? Note that the solution of this end of potential line instance, so all the sinks and all the source, corresponds to sinks in the original SOPL instance. So in some sense, we're good. But there is one missing piece. Where do you put the source? This end of potential line instance doesn't have any source. A quick fix would be just to add the source somewhere and link it as follows. But now you've created a new sink, which corresponds to a source in the original SOPL instance. And so this is not a valid solution. So clearly this reduction fails, but it tells us something important. The only crux now is that we need to somehow hide a new source in our instance. And for this, we will use the bijective pigeon instant as a reduction gadget. So, okay, this is our third idea. So as input, you get an SOPL instance and a bijective pigeon instance. And we start by just adding a source to our construction. And now we put 2 reversed copies of the SOPL instance and 2 original copies of the SOPL instance, so not reversed. And now we're going to link them using the bijective pigeon instance as follows. Okay, so this we call our EOPL instance. And notice how we've used our bijective pigeon instance to hide the new source. In particular, it allows us to pass from 3 sinks to 2 sources. And in this way, we can hide the new source. Note that all the solution of this EOPL instance corresponds to either a solution of the SOPL instance or a solution of the bijective pigeon instance. And here it was really crucial that both the SOPL complete problem and the PPAD complete problem were problems on the grid, something you could assemble together. And actually, this is more or less the wall proof. You just need to be a bit careful with where you place the sinks, etc., but those are just technicalities. So it's basically just a proof by picture. Okay, this being done, here is how the TFNP hierarchy with the main subclasses looks like in 2022. And I guess the question is, can we find further collapses? And this is not part of this work, but let me just say that continuing on the pioneer work from B Meta from 1998, we were able to show that, so we've completed the picture and show that all those classes are separated via oracle. And this, even something stronger, that there is no black box reduction between those classes. And note that all the reduction that have happened in the past, the CLS1, the SOPL, and the EOPL, were black box, right? We were just looking at the input-output behavior of circuits and never looking really at the internals of it. So in particular, it means that PLS intersect PPAD doesn't or is likely not to collapse all down to unique end of potential. Thank you.